请坐。
没有，没关系。
继续哈，我们大概还有1个钟头，我们大概讲到11点半，那剩下的时间呢就是问问题，所以从现在就开始要想问题。我们没有问够问题不下课的，不结束。Hello. Okay, so I am now going to tell you about a really fascinating topic of black holes. This is where my work is focused. And I'm going to ask the question, how do black holes grow? And the basic answer to this sort of simple answer, is they swallow gas. When they swallow gas, they gain its mass and then grow up because of that. However, the key here is that when they swallow gas, they can release huge amounts of energy, enormous amounts of energy. Now, this may seem a bit strange that you can release enormous amounts of energy from this gas, but in fact, it's actually quite simple. It is the same as hydroelectric power. So, for hydroelectric power, who has heard of hydroelectric power? Who knows what this is? 水力发电。Yes, they all heard of it. Okay. So the basic idea is that you have a dam, and you have water, and the water falls down some pipes, and you get this energy. And what you are doing is you are taking gravitational potential energy from the water, you're taking gravitational potential energy, and you're turning it into electricity. So in a black hole, I will tell you about this later, but if we take some gas and it falls into the black hole, the gas has a huge amount of gravitational potential energy that can be released. Now, how much do I mean by a huge amount? So I did a quick calculation, and I Googled some information about Taiwan, and we find that if you take 1 kilogram of matter and you drop 1 kilogram of matter into a black hole, you can power all of Taiwan's energy needs, all of the lights, all of the air conditioning, all of the cars even, for 2 weeks. That's from 1 kilogram of matter. The actual amount of energy that corresponds to is 10 to the power of 16 joules. That is 1 with 16 zeros after it, joules. So an enormous amount of energy is released when you drop gas down a black hole. Now, how does the gas actually fall into the black hole? Well, it typically has a problem, because if you look at this picture, it actually, remember, black holes are very small. So if gas is flowing towards the black hole, it typically will not hit the black hole head on. It will actually miss the black hole, and it will go into orbit around the black hole. So the gas is actually orbiting the black hole, typically. And it will form a disk. It will form this disk here. So this is a disk of gas, and the disk is orbiting around the black hole. Now, just to show you one example of some of my work, this is a computer simulation of how gas actually orbits around black holes. And an important fact about the gas going around a black hole is the gas becomes turbulent. It the gas flows become very chaotic. And in fact, it is this turbulence in the gas that allows the gas to gradually fall into the black hole. It is the fact that the gas, it's the turbulence that allows the gas to fall into the black hole. Just 2 weeks ago, there were two American professors, John Hawley and Steve Valgus, who won a huge prize. They won the Shaw Prize, which is sort of as big as the Nobel Prize. And they won it for this work, for understanding how gas actually flows into the black hole. But we can, in my research group, we do computer simulations, we do computer calculations of how the gas orbits around the black hole and how it flows in when it becomes turbulent. So turbulence is a very interesting phenomenon to study, and we can use these simulations. So this simulation was done on a very big computer, similar to the computer I showed you, not quite as big, but the simulator.
这边是这样，就是大概就才2个礼拜前哈，那个有一个奖项，我相信我们大部分都没有听过，是邵逸夫奖。那邵先生他就是提供，而且他这个奖项就是诺贝尔奖的那个等级，他的钱啊跟他的那个做的工作都很优秀，但只给天文。但是我们都没听过，对不对？因为我们的新闻都在报哪一个小模啊跟谁出去啊，或者那这个邵氏啊，或者是邵逸夫奖呢，2个礼拜前就给了这2位美国的教授，就是为了他们的计算的研究工作，计算东西怎么样在黑洞里面怎么样掉进去啊，就这个事情。那其实我们今天这个奖当然小很多了，但是也是一样，媒体对这个比较没有兴趣。 对，唯一受惠听得到就是你们职业了。
So, as the gas orbits around and as its turbulence develops, the gas gets hot. It gets hot because the physicists say there is dissipation, meaning that as the gas gets turbulent, you have gas rubbing against itself, and it gets hot. And as it gets hot, it also flows inwards. And its gravitational potential energy is being turned into heat in the gas. So as the gas flows inwards, it gets hot. And because it gets hot, it starts to glow. It will shine. And so, in fact, a nice... Yeah. So this is actually probably a fairly realistic picture of what a black hole would look like. You have an accretion disk, this disk of gas orbiting around the black hole, and as it gets closer to the black hole, the disk will glow brighter. So this is how that tremendous energy actually comes out. This energy comes out through the radiation that the light that this is emitting as it gets hot. Now, one other thing that you see on this in this drawing is this strange feature here. I will talk later about this, but this is what we call a jet. We don't understand jets, really, but somehow we know that black holes can take some of this gravitational potential energy and they can channel it, they can funnel it into a beam or a jet of gas that shoots upwards. So you have this tremendously fast flow of gas that's shooting upwards, perpendicular to to appreciate.
刚才刘荣教授做了一个很好的比喻，就是像那个水力发电，重力把它变成热能和电能啊。那在这边是黑洞把东西吸附，万有引力非常弱，可是因为空间很大，万有引力场也储存很多能量，所以当它吸进去了以后呢，东西会加速掉得很快。那一个加速掉进去的过程，或直接彼此摩擦等等，就会产生热。所以这是假的一个画，中间那个黑洞掉进去的那个盘状结构，我把它叫吸积盘，因为它在吸东西。可是很有意思，详细的过程不是很清楚，但瑞文教授也在做这方面的研究，就是在掉进去的过程当中，不是所有东西都掉进去变黑洞，有一大部分被甩出来，像个两极呢，这个喷流的这个 jet 是一个非常非常高能量的现象，因为很多能量把它聚集成为在一个很小的距离把它喷出去，所以它会有极高能量的辐射。
So it turns out that a particularly important form of energy that is produced by this disk is actually X-rays. The gas as it orbits a black hole gets so hot that it actually puts out a lot of energy as X-rays, extremely hot. So just to remind you what X-rays are, let's look at our spectrum again. Again, this is visible light, this is the light we can see with our eyes. And if we go to the blue part of the spectrum and keep on going, you get to ultraviolet. Ultraviolet is what gives you sunburn. The sun hits you and you get sunburn. This is the UV, ultraviolet. If you keep on going, you get to X-rays. X-rays are what dentists use to take your teeth or bones. So this is where black holes can put out a lot of energy in the X-rays. So we want to study that. We want to study the X-rays from black holes. We cannot do that from the surface of the Earth, from anywhere, not even in the desert, not even when we have dark skies. Why is that? Why can we not study X-rays from the surface of the Earth?
黑洞辐射很多 X 射线，人家问你说，但是 X 光 X 射线不能在地球上面研究，为什么？
Exactly, yes. So the atmosphere on the Earth is a shield. It protects us from X-rays. X-rays are very dangerous. When you go to the dentist and they take an X-ray of your tooth, the dentist goes away. Or the dentist wears a big lead. X-rays are dangerous. So it is very good that the atmosphere protects us from X-rays from space. It's a very good thing. But if we want to actually study X-rays that are coming from black holes, this is where we have to go to space. We have to get above the atmosphere. So in the very early days, in the 1960s, 1970s, what astronomers did is they used small rockets like this. They would use a small rocket. They would put an X-ray detector at in the tip of the rocket, and the rocket would go straight up. It would spend about 5 minutes above the atmosphere, and then it would come crashing down. And this is a picture of the rocket once it crashed down. And the detector, you put on a little parachute, it detects it. And the astronomer would have to get into a helicopter, and they would have to find, they would have to search for the detector, and they would then study the information in the detector. So this was good, and this led to many discoveries. This led to the discovery of the very first black hole that we knew about. This led to the discovery of what's called Cygnus X1. It's in the constellation of Cygnus, and it is the first X-ray source discovered. That's why it's Cygnus X1. And this is a picture of Cygnus X1 in X-rays. It's this bright X-ray point. And after much study, we came to this picture for Cygnus X1. We know that Cygnus X1 is a black hole. It has a normal star, a very large normal star, near it, like this, a blue star. And the black hole is tearing gas off that star. And the gas is being torn off the star, and it spirals down into the black hole. When it does that, it produces a lot of X-rays, and that's what we see. So when Cygnus X1 was first discovered, there was a lot of study of this. People took normal telescopes, they discovered the star, and there's a long story here, but eventually determined that this was a black hole. This was the very first black hole discovered. Now, so this is all very good, but this is a lot of work to do for 5 minutes of data. Okay. You build the whole rocket, you build the whole detector, and you get 5 minutes. It is not very efficient. So of course, what we do now is we build satellites, and we put the X-ray telescopes in satellites, and the satellites can orbit the Earth for many, many, many years, and we can get data for many years. So this is one of the best X-ray telescopes right now. This is the Chandra telescope. This is that's the artist impression of the telescope, and this was launched on the space shuttle. So this is a picture of this. Actually, a picture of the launch. It was a nighttime launch of the space shuttle. So Chandra is a very big satellite, and this is why it took the space shuttle to launch. Okay, so what can we do now that we have X-ray satellites? So much of my work is using data from X-ray satellites to study black holes. And just to show you an example, this is one particular galaxy. This is a galaxy called NGC 3783. It's not a very memorable name, but this is one particular galaxy, and we know that this galaxy has a black hole in it, and the black hole is swallowing gas. But when you look at the visible picture, this is just a visible picture of the galaxy. What you would see if you looked through a telescope with your eye, there's nothing very special. You just see a little faint galaxy. If we look with an X-ray telescope, and I will show you the picture from the Suzaku telescope, which is another telescope, we see this. So this is an X-ray picture of that same galaxy, and what we find is a very bright X-ray source. In fact, the X-rays are all coming from a small point here. What you are looking at here is the bad mirror of the telescope. Focusing the X-rays is very difficult. It's very difficult to focus X-rays. To build an X-ray telescope is very difficult. So what you are seeing are distortions of the image from the X-ray telescope.
对，这边就讲到说，要研究天文现象，常常需要不同的波段，有不同的机制、不同的区域。那研究黑洞呢，就刚刚讲很大的万有引力的位能呢，变成了辐射的能量，很强、很高能，那常常在 X 射线，所以就常常用 X 射线的望远镜。X 射线地面不能看啊，所以到了天空，一直是放那个火箭，或者就用人造卫星。Chandra 是一个人名，他是印度的科学家，研究白矮星这个，所以当时望远镜用他的前德拉望远镜。那这一张是日本的一个 X 射线的望远镜，叫做史扎古。那这个刚刚解释说为什么这其实黑洞其实很小，那为什么像这么大一坨呢？是因为我们学过，要东西要成像嘛，要不然就用折射嘛，要不然就用反射，对不对？X 光不能反射，因为 X 光太强了，你没有东西，它光线会打过去，所以我们在照 X 光形象片嘛，它会穿透过去，所以 X 光很难让它去挡住它的光线，要用很小很小的角度，所以 X 光望远镜的影像品质都不好，所以它就是明明是一小的，它成像起来变成很大一堆的。
So when we look at the X-ray emission from one of these black holes, there are many things we can do to study it. And one of the things we can do is to look at the spectrum of the X-rays. In other words, we can see how many X-rays are coming out at each frequency or at each wavelength. We can look at the spectrum. Now, this is a very interesting thing to do, and let me just try to describe to you just a little bit some of the things we do. Some of this is a little bit technical, so don't worry if you lose the details. One of the things we can do is we can use the spectrum to study the orbits of the gas around the black hole. So just to this is an animation showing, for example, a blob of gas or a piece of gas going around the black hole. And what you are seeing here is a representation of the spectrum of some of the emission from that gas. And basically what happens is you are looking at go to this image briefly. The gas is swirling around, and so some of the gas is approaching you. So the gas on this side is coming towards you, and some of the gas is going away from you. So you get something called the Doppler effect. Now, you all know the Doppler effect because you have heard police cars or ambulances go past you. So they go. So when they're coming towards you, the pitch is higher. And when they're going away from you, the pitch is lower. And that's the Doppler effect. And that's for sound. That happens for sound. But exactly the same thing happens with light. So when something is coming towards you, the light that it emits is shifted up in pitch, shifted up in the frequency of the light. When something is going away from you, it's shifted down in the frequency of light. So we can actually see that effect in spectra, the X-ray spectra of these black holes. In the light that's coming towards us, or the light from the gas is coming towards us, its light is increased in frequency or decreased in wavelength by a little bit. It gets a little bit bluer, if you like. And going away from you, it gets a little bit redder. Now let me show you some real data. This is a real spectrum from one of these, from this same object I showed you, the same galaxy. And what you see here is there is a particular characteristic frequency of light. It's called an emission line. There's iron in the disk, and the iron is producing a particular emission line. And what you see is that some of the emission is blue shifted, some of the emission is shifted up in frequency, and a lot of emission is shifted down in frequency. Now the reason why there's a lot of emission shifted down is that it's not only the Doppler effect you're seeing, you are also seeing a really fascinating effect of time running more slowly as you get back close to the black hole. So one of the strange predictions of Einstein's theory of general relativity is that as you get closer to black holes, time runs more slowly. And that also affects the frequency of light that the matter is emitting. As you get closer to the black hole, the frequencies that are being emitted are shifted down because the time is running more slowly. And so you actually can see that in this spectrum. You can actually see that this long tail on this emission line is because time is running more slowly close to that point.
这个系列的演讲我认为最棒的一些事情，就是可以看这些很肮脏的资料，不是所有事情都在教科书里面很漂亮做出来，这是真正取到的资料。你看，非常杂质质量大。宇宙中间含量最多的东西是氢，可是在黑洞这么样剧烈高温的环境里面，氢全部都是游离的，对不对？那我们知道，在电子啊，它绕在原子核里面一定的轨道。它从一个轨道跳到另外一个轨道，然后就做出一些线，它只有那个能量发射出去，没有氢呢，因为氢都全部游离了。那是什么？这是铁，铁的其中因为铁有26个电能啊，所以它可以把它发成铁，要很高温呢，才可以让它激发，那就是铁的线。那刚刚讲到一个杜普的效应，大家其实都很熟悉了，对吧？杜普的效应，坐在车子里面的人听到单一的声音，啊的声音。可是向着他来的人，他原来后面的这个声音啊，向着他来追过了原来的声音，本来晚到的声音现在找到，就频率就增快，这就是杜普的效应。利用原来的实验室里面，我们看到一条光谱，原来在这个地方，这个能量，这个波长，可是真正观察到呢，除了这条线以外，还有一个很长的尾巴这个现象。除了是因为杜普的效应以外，另外还是在一个时间延时，就是跟相对论里面，就是说，当你掉到黑洞里面去的时候啊，你越掉进去的时候，你会越来越慢，你的时间啊会越来越慢，你永远不老，会老得非常慢。这是一个很特殊的一个现象，因为有了那个时间延迟的现象，黑洞就会有特殊的现象，这其中一个造成了一个这样观测到的一个现象。
So we can learn a lot from these spectra. Another thing we can do is, again, if we take this X-ray emission, we can see if it is steady or if it changes with time. And the answer is it does change with time. It can change very quickly. So that's dark, but you can see here a graph of how bright the source is versus time. And from here to here is about 4 days. And you can see that in the period of 4 days, the brightness has changed huge amounts. There are big flares